and the National Academy of Engineering of Korea. So this is Lalitambika of IIT Madras, formerly distinguished scientist of the Indian Space Research Organization. I'm very pleased to coordinate this workshop, and I thank the academies for the opportunity. The honorable members of the two academies and the related experts in India and Korea are participating in this workshop online. So the theme of this workshop is very significant, with new technologies coming into spacecraft for Earth observation, and also information gathering and dissemination all gathering and gaining more and more importance. And it's also being held at a very apt time because both India and Korea are putting in very significant efforts on space technology. In India, National Space Day commemorating the Chandrayaan-3 landing at the lunar South Pole falls this week. And ISRO has just launched the Earth Observation Satellite EOS-08. And the Solar Observatory Aditya L1 has just completed its first halo orbit around the Sun-Earth Lagrange point. INSAT 3DS meteorological payloads have started imaging the Earth, while Korea has established its full-fledged space agency, and the COMSAT series of satellites continue to provide high-resolution Earth imagery, Danure is in lunar orbit, and so many other achievements. So we may start with the two leaders of our societies. First of all, I would like to introduce the INAE President, Dr. Indranil Manna, who is also Vice Chancellor BIT Mesra, India, and the former Director of IIT Kanpur. Professor Manna will now give the welcome address. Let us give him a big round of applause.
Thank you very much, Dr. Lalitambika. A very good morning and good afternoon. And in my own state, we say Johar, which means welcome. So welcome to all of you. We are extremely happy that this Indian National Academy of Engineering and National Academy of Engineering of Korea, the collaboration between two of us has been progressing very steadily for the last 7 or 8 years. The first meeting was held in Bangalore in 2017, and since then, every year we meet in person, physical interaction used to happen, but since the pandemic, it has become now hybrid. We'll try to resume physical visits very soon. But I've been associated with it since the very beginning, and I'm very pleased to report that we have covered very important topics. We began with high temperature materials for the first two sessions. Then we went into the material system engineering in various space exploration activities. That was in Hyderabad 2019. 2021, we talked about what is next in aerospace engineering and advanced materials. 2022, we discussed about advanced materials for sustainable growth. That was hybrid. We assembled in Kolkata and the Korean team in one of the cities in Korea. Last year, we talked about space development and a hybrid meeting, but was very successful meeting. In fact, Chairman ISRO addressed, and we had very excellent presentations, and certain very important recommendations came out of these interactions. And this year, as Dr. Lalitambika just explained, we are looking at the use of satellites for observing the Earth. And when we say observing the Earth, it's not just one or two facets. We are talking about a whole range of very important applications and engineering aspects like climate, weather, mineral resources, water, glacier, various natural resources, even natural disasters, how to mitigate them or take care of them. Traffic movement, of course, then various borders and other safety security measures. So there's absolutely endless scopes of application of this remote sensing possibilities. We are very happy. We just heard that India making big strides. Korea also has become one of the leading partners in space exploration. So the two academies, they have been working in close tandem for the last 7, 8 years only on this count, but we have longer history of even historical collaboration running for centuries. But leaving aside that, This time in Helsinki, in the sidelines of the Gates meeting, the two academies met and had very little discussion. And I propose that let's go beyond the meetings and interaction and start collaboration, which leads to some very tangible output. And I propose that there could be some joint student supervision or exchange and collaboration at expert level. But that we'll discuss in another occasion. But I would like to certainly record our deepest appreciation on behalf of the Academy to all those who are participating, in particular, Dr. Kim, who is the president of NAEK and a very well-known expert in the field of electronics materials, a former boss of Samsung. Then we have Dr. Jojin Lee, we have Dr. Jai Ik Wo, and from the Indian side, we are very proud to have Dr. Shailesh Naik, a very well-known expert in earth sciences, Dr. B.N. Suresh, a former president of INAE, and also a very well-known expert in space technology, Professor R.I. Sujit from IIT Madras, and of course, Dr. V. Lalitambika is herself a very well-known expert in this field, and Dr. Chanming Lee. So I certainly would expect that this interaction today and tomorrow is going to lead to some very important outcome, and which will be useful not only for these two countries, but the world over in this space technology. Let's look forward to a very fruitful interaction. Thank you very much, and Jai Hind. You're muted, Dr. Lalitambika, you're muted.
Thank you so much, Professor Manna, for that welcome address. I would now like to invite President of National Academy of Engineering, Korea, Dr. Kinam Kim, who also served as the CEO of Samsung Electronics and, as Professor Manna has mentioned, is a renowned expert in the field of materials and other areas, for the opening address. Let us welcome Dr. Kinam Kim with a big round of applause.
Ladies and gentlemen, good morning and good afternoon. It is my pleasure to welcome participants from India and Korea to the 7th INA and NEC workshop. It is quite meaningful that NEC and INA have been building a networking platform since 2017. Despite various changes and challenges over the years, we have continued the collaborations between Indian and Korean engineers. I would like to express my deepest gratitude to INA for your effort and dedication in hosting this year's workshop. I am especially grateful to President Indrani Manna for his strong support and leadership. Following last year's workshop on space development, we are focusing on more detailed theme this year, that is, the utilization of satellite imagery. You may remember that our workshop last year was held just right after the launch of Chandrayaan-3 by ISRO. In February of this year, ISRO successfully launched the INSAT 3DS meteorological satellite. This satellite is expected to provide vertical profiles of the Earth's surface, which aligns with the topics of our workshop. Korea has also achieved significant milestones this year. In May, the Korean government established the Korea Aerospace Administration to promote the aerospace industry. Additionally, the Ministry of Science and ICT hosted Committee on Space Research, or COSPAR, last month, where more than 3,000 experts from space developing institutions in 55 countries shared valuable insight. Korea's commitment to this area is stronger than ever before. External Affairs Minister of India recently visited to Seoul to co-chair the 10th India-Korea Joint Commission meeting, which clearly marks an enhancement of the relationship between our two countries. Recent advancement in defense and trade cooperation, along with the increased investment from Korean companies in India, signal a positive future for collaboration in the aerospace sector. In light of this timely development, we look forward to strategies and suggestions that will guide our aerospace industry. As we embark on this journey, we anticipate fruitful discussions and the exchange of the ideas that will drive the development of satellite technology and its applications in both Korea and India. I believe that by continuous upgrading our approaches and combining our expertise, we can pave the way for a brighter future and seize opportunities ahead. I hope you all have an enjoyable workshop. Thank you for your kind participation. Thank you.
Thank you very much, Dr. Kim. So now we have heard from both our leaders. We had the welcoming and opening remarks, highlighting the engineering skills and capabilities of our two countries. And there are certainly many technological areas where the two academies can work together for the common good of both the nations and also of all humankind. So now we will move on to the keynote address. We have two keynote speakers who are among the leaders in the domain of science and technology and also Earth observation. The first speaker is from India, Dr. Shailesh Naik, Director of the National Institute of Advanced Studies and Chancellor, Terry School of Advanced Studies, who is also the former Secretary of the Ministry of Earth Sciences and the former Director of the Indian National Center for Ocean Information Services. The title of his talk is Observing Earth from Space, Benefits for Humanity. And we are sure to benefit from his vast experience in this domain. Please welcome him with a big round of applause.
Are on mute.
You're muted. Dr. Naik, you're muted.
Thank you very much for this nice introduction, and good afternoon to all my Korean colleagues and good morning to all my Indian colleagues. I'm extremely grateful to Professor Indradil Manna, the President of Indian National Academy of Engineering, for inviting me to participate in this very important workshop on the current status and cooperation plan for the satellites for observing the Earth. I think, as my previous speaker has mentioned, the topic is very apt and very, very timely. The advent of satellites in 1960s allowed the Earth to be viewed in a synoptic, repetitive, and multispectral, and now even hyperspectral modes, and provided insight on Earth system processes, environment, and resources. With the advancement in computing, the satellite data are now routinely assimilated in numerical models to understand weather, climate, hazards, water and carbon cycles, terrestrial, coastal, and marine ecosystems, polar regions, human settlements, agriculture, infrastructure, and many, many more. There are more than 30 countries who have now owned satellites launched for the various applications. It is vital to collaborate with each other to address the global challenges of sustainability, especially related to climate change, water and food security, education, inequality, and poverty elevation, as well as planetary research. Spacefaring nations should collaborate to generate new knowledge about our planet and develop innovative products and services for the humanity. I would like to describe few areas which India and Korea can consider to collaborate to provide space-based products and services for the global community. Satellite data, as any other scientific data, should be considered as a raw material. But unlike other raw material, they have a perpetual value. When satellite data is used cleverly to develop new and innovative products and services, they become a vital economic and/or environmental input. Such products and services meet user requirement, either government, industry, or citizens. Their economic value or the benefit to the country increases manifold. However, there are no standards developed for specifying characteristics of data from the various sensors and payloads. Each sensor manufacturer, either government or private, defines specifications quite differently, and user does not get clear idea about likely performance of the sensor and the utility of the data products. Dr. George Joseph, the father of electro-optical sensors in India, has proposed the parameters which should be considered for standardizing the sensor specifications. They are: the spatial domain should be specified in terms of instantaneous field of view, ground sampling distance, modular transfer function at IFOV, etc. The spectral domain should be defined as a central wavelength as well as the bandwidth and out-of-band contribution. In radiance domain, the saturation radiance, the signal to noise ratio is 90% of this saturation radiance as well as at the 10%. Number of digitization bits and the calibration accuracy. At the spacecraft level, the temporal aspects, the temporal resolution, as well as the revisit capability, and as well as, lastly, the data integrity, the compression levels which is used in this. It is imperative that we need to have a dialogue in standardizing this specification so user gets uniform kind of a performance and knows that what particular sensor will be able to provide for. We are now getting increasing volume of satellite data both from government and private entities and continue to increase in the future. However, the availability of large volume of data do not always guarantee its usability. There is ample scope to build innovative applications on big data to increase its usability. Big data and artificial intelligence, a revolution that is already transforming how we understand the earth in which we live. Big data analytics have an ability to harness information in innovative and novel way to produce useful insight. There are several areas such as climate change, public health, astronomy, etc., where this technology is making significant impacts. Such data sets have some intrinsic hidden value. We need to discover it and use it for, as for example, climate services, sustainable development goals, etc. In India, we have 40 years of INSAT data. Can we use these data sets to find signals of climate change as changes in cloud patterns which may have occurred and use this information for the validation of the climate models? Another example is a crop yield and weather-based insurance cover offered by insurance companies to farmers. A mix of satellite data, ground data, artificial intelligence, Internet of Things, and big data analytics can be used to create a map-based digital framework to predict crop yield estimates, which can have a very high accuracy. Such product can be useful to get bank loans, crop insurance premiums, good price for the crops. It can be also useful for the district authorities, decision makers, banks, and large farmers, etc. Sustainable cities is one of the major goals under UN Sustainable Development Goals. Satellite imagery analytics can provide virtual display of landscape from global scale processes to fine scale reviews of cities and buildings. Such display has tremendous impact on the society as individuals, and as the individuals are able to relate themselves with the environment in which they live. There is also need to build a single digital cadastre along with 3D building models using high resolution satellite data for the use of government, industries, and civil society. The geospatial industry can collaborate to generate such databases. ISRO's Women portal also has been providing a single gateway access to data, information, and services to support the government, industry, and citizens. Sustainable utilization of marine living resources, especially fishery, depends on the estimation of biological sustainable limits. The variation in interannual yield depends on the understanding of the physical, chemical, and biological processes of the system. Satellite-based sea surface temperature, chlorophyll A, sea surface wind, and sea level, along with the conventional observation, provide insight into physical and biological interactions, and when coupled with physical models, can provide short-term and annual assessment of pelagic fishery. Such species-specific models are to be developed. Sea levels are increasing at accelerated rates and affect human settlements and coastal environment. Sea level rise has been inducing hydrogeomorphic processes through increased tidal range and prism, alter sediment transport patterns, change shorelines, and affect low-lying coastal areas and ecosystem. A development of a model by combining a digital shoreline analysis system, the 3D and 4D hydrodynamic modeling is needed for coastal zone management. One of the challenging issues is to understand hazard generating processes for earthquakes and landslides. The measurement of modeling of stress at the plate boundaries through navigation satellites, continuously running ground-based GPS, and estimation of strain from SAR interferometry and high-resolution topography from Cartosat can provide insight into the crustal deformation and active faults for seismic landslide hazard assessment. The importance of datasets from orbiting satellites with airborne, in situ, and ground-based geophysical measurements are useful to fully characterize the spatial and time scale of triggering of earthquakes. The systematic measurement of long-term strain accumulation of the crustal origin is the present need to provide resilience from the hazards. The planned joint mission, NASA-ISRO SAR mission, NISAR, will provide land surface changes globally. Another issue is why we need to define or refine the datum, a very critical input for all geospatial applications. The changes in datum are important even if they are small in magnitude. The Indian plate moves around 4 centimeters northeast every year, while the Eurasian plate, of which Korea is part of, moves around 2 centimeters per year. The transfer of large mass, the due to melting of ice sheets and depletion of groundwater, and goes to mass moves from land to sea. All these aspects need to be taken into account while getting the datum right. The improved geoid model and spatially dependent accuracy statement will provide high confidence in measurements. Such exercise can provide a centimeter level positioning service. And this could be one of the major area of the research. The effective use of satellite in climate studies will require calibrated products. The calibration sites near Kavaratti in Arabian Sea for the ocean color, in Kutch Desert for the inset, and for optical and microwave data in the campus of Shadnagar of National Remote Sensing Center can be used for the intercomparison of sensors and paving way for the development of calibrated products. It may be useful to have a separate workshop between these two countries to define the requirements of the calibrated products. There is also need to identify a new or continuity of the sensors for various applications. The World Meteorological Organization has determined that the global wind profiles are essential for operational forecasting on all scales and at all latitudes. It has been realized that the further improvement in forecasting weather will depend upon a simulation of wind profile into models. The impact of wind observations, such as radio sonde, have larger impact than the property of mass, such as temperature and humidity, on a short-range forecast, as well as for the climate change research. The Atmospheric Dynamics Mission, ALOS of ESA, have ultraviolet LIDAR, which provided first-time winds from the surface to stratosphere, up to 30-kilometer height, which was very useful for improved weather forecasting. However, it has certain issues and at present is not functioning. It is a good idea to develop such wind profilers for the global use. The other area is to development of microwave radiometer, a SAFIR, working at 183 gigahertz, which was on the Megatropic satellite joint Indo-French initiative, showed that its data used improved drastically the humidity and wind forecast in the troposphere. This has been now discontinued. The other microwave radiometer working at 6.6, 10, 18, and 21, which was on OceanSat 1, provided the sea surface temperature and marine atmosphere parameters. It is now known that the sea surface temperature retrieval from or at 7 gigahertz is more accurate than any other frequency at all latitudes. Also, the polar regions, which are becoming more important to monitor for environmental changes, the 7 gigahertz channel can provide very accurate SST. However, this is also not continuing. There is a strong case of developing this radiometer for the future missions. There is also need to build a satellite-based Earth system observatory for data in a continuous at user-specified specifications and in a timely manner, which should include the payloads to characterize atmosphere, hydrosphere, geosphere, cryosphere, and biosphere, and their interactions with anthropogenic activities and vice versa. Many collaborative initiatives between India and with the US and France have yielded development of sensors which led to useful products and services. India and Korea should identify likely payloads to be developed which are useful to the global community. India has developed small satellite launch vehicle which can provide launch services on demand. The successful launch of SSLV recently demonstrated a capability to place small satellites up to 500 kg in a low Earth orbit up to 500 kilometer is a very good candidate for the cooperation. The technology of this launch vehicle will be transferred to industries and will be available for the commercial launches. The focus of collaboration should be on globalization. The current policy of India, which allows FDI flows and technology in all fields of the space sector to India. the investment in research and development of new technologies, support to startups, big and disorganized data, development of algorithms, innovative applications are being encouraged. The new areas such as digital humanities, forecasting conflicts, energy transition, climate information from local to global scale, the changing water cycle, blue economy, health, system for decision makers are good candidates for collaboration. Lastly, the societies are primarily built on technological advancements. Technologies, especially space, communication, digital, had led to individuals, groups, and countries to modernity, empowerment, and prosperity. Technology has to be understood in social contexts. It is the people who make decisions about how technology is to be used. The strategy should be how technology can convert or transform or translate the capabilities and functioning of human dignity, excellence, and enhancement. I am sure that the collaborative efforts between India and Korea will lead to achieving sustainability of the planet Earth. Thank you very much for this opportunity.
For that insightful speech and for sharing with us the diverse benefits of Earth observation for humanity, the technological advancements in the domain, importance of global cooperation for understanding our planet, and also for outlining the areas where our two countries can collaborate. Thank you very much. Now, let us move on to the Korea side leader, Dr. Joo Jin Lee, who is the chair, Advisory Committee on Science and Technology Diplomacy, and also the previous president of the Korean Aerospace Research Institute. The title of his talk is The Status of Satellite Development in World and Korea and Climate Monitoring. Please welcome Dr. Joo Jin Lee with a big round of applause.
Thanks a lot, Dr. Suresh. First of all, we suffer from also hot temperature in these days. So, 안녕하세요 for the Korean participant and namaskar for the Indian participants. I am Joo Jin Lee of the Korea Aerospace Institute, the former president, and it is my honor and a great pleasure to join this Indian and Korea Academy of Engineering workshop. I'll pop up my the PowerPoint for this presentation. All right. As our Earth has confronted the severe environmental change, such as natural disaster like a deluge and a frequent earthquake, and artificial disaster like a war, the monitoring of these disasters using our Earth observation satellite is becoming more important and imperative. Today, I'd like to overview of the global trend in satellite development and also Earth observation and climate monitoring status and Korea space development status. The technology and the industry of the satellite has progressed to become a more specialized and more global and more economical. For the diversity and then more the popularization of the satellites, the miniaturization should be a more economical way. These statistics shows the 4 times in number of the satellite expected in next 10 years prove this the effectiveness of the miniaturization. And then with this, the miniaturization, the constellation of the satellites are becoming more popular for the continuous monitoring. And also you see with these, the numbers for next 10 years is a major part of our satellites. And for the industry side, as the large-scale communication satellite for the constellation, the industry can be possible for the mass production. You see the pictures is that SpaceX is manufacturing 120 satellites per month. Also, the technology of the Earth observation satellite has been developed as adaptation of the AI technology, and then the advanced, even to apply this kind of image intelligence satellites for real-time monitoring. And then for the climate monitoring technology, we can also develop those monitoring the greenhouse gases and exact temperature distribution, and also accurate height of surface. And in Europe also, they use the satellite for the monitoring all those climate change, and also in situ, like ground measurement data for the more exact the monitoring scale. And for the communication area, utilization of satellite has been spotlighted again to be used in the battlefield and then a disaster area due to the no need of the ground antenna. And also a combination of the communication satellite in LEO and medium Earth orbit and also geostationary orbit could make possible for the usage of the communication from satellite to the direct to a smartphone. And then for the higher data rate and also secured data rate transmission, the laser communication technology has been developed and being tested recently around the world. And some examples is NASA has tested in 2013 for the lunar communication relay, and then also in 2021 they made also the GEO and LEO satellites communication relay. So Europe has a similar test in 2022. And also in our Asia, China, Japan, and Korea and India had a similar test for the satellite the relay. And now I focus on the Earth observation and climate monitoring area. The Earth observation in the United States has developed and operated the most wide range of the Earth observation satellite since 1958. The NOAA is also the earliest organization which had surveyed the global weather continuously. In 21 centuries, this NOAA's mission is for the long-term record of atmospheric gases and also aerosol particles and cloud and surface temperatures and radiations. And also the NASA has performed Earth observation with some development of advanced technology related with the Earth observation. And then the technology advancement is focused on the higher image resolution and also hyperspectral capability to enable the detailed and diverse data collection. Some examples of this satellite image for the flood monitoring is like an emergency case, such as disaster. Satellite can provide real-time data and image. And also this photo shows that is the interferogram data from the SAR, which is a earthquake in the Napa Valley in 2014. And with this data, they can measure like a 5 centimeter and 9 centimeters movement of a Earth surface. And next example is the precipitation of the United States. They compare like this early of 1990s and even to the in the 21st centuries. The data shows for the dark brown color is a almost 12.5 drier data, data, and this dark green is a 12.5 wetter, so it's a higher precipitation. So this data can applied or predicted for the rainfall and flood like this. And this photo shows this air quality of our whole world, and this yellow and red spot is in the popularized area, the more the pollution of the air. And also Earth observation in Europe. The European Space Agency, they made their organization with the name of GMES, Global Monitoring of Environment and Security in 2005, and they changed their organization name as Copernicus in 2012. They made some more accurate the data that combined the data from satellites and also the in situ, the ground, the measurement data. And also they operate like this Sentinel series satellites and also the MBSat. And the monitoring service is applied for marine and land and climate change service and etc. And also the other example is this is for the monitoring of our Earth, the surface temperature. This the data of the 1996, and this data compared with the 2020, and you see this the North Pole area, Siberia has this is a hotter for last 24 years, and further this brown the graph shows that their simulated data and the black the line is made of observed, and if you see that from 1996 to the 2020, almost 0.6 or 0.7 degrees increased for this average temperature. And for Earth observation in Japan, also they made such a continuous and long-term monitoring with their satellites, named ALOS, is for the measurement of the Earth surface displacement with the SAR data. And then for Explorer, they measuring the aerosols and radiation. And with a frequent earthquake in Japan, also they made a big efforts to measure those also interferometric displacement, and their accuracy is around 3 centimeters with their data. And also India is also island. They made almost 40 Earth observation satellites from the 1988 and launched such many satellites. And in recent years, they made such a high resolution image satellite, the Cartosat. And also last year, India launched the small set for the spectrum monitoring purpose, and that is a kind of a some advanced technology. And then they made a utilization for the meteorological support with the INSET series, and for this also they made the continuous monitoring. And also I learned India made such a deep space exploration, and in about 10 years ago they made a Mars orbiter mission, and then in last year with a Chandrayaan-3 they landed on the moon, and this picture I learned taken on the moon with their rover named Pragyan. And next, I'd like to introduce our Korean space program. And we started our development of the satellites in the early about 1990s, and now is almost 20 satellites launched and operated for the main purposes of Earth observation and also the meteorological purpose. And the CASA, Korea Aerospace Administration, was inaugurated in last May, and it's opened with the existing our research institute, Korea Aerospace Research Institute, and Korea Astronomy and Science Institute. And the CASA will enhance and expand our national aerospace development program, and also strengthen our private sector development, as well as the CASA will promote international cooperation very actively. For our Earth observation satellite, Korea has developed with a series of the COMSAT. And one example with the high resolution of the COMSAT is a 0.55 meter, and this photo shows our new administrative city, the Sejong, in south part from the Seoul. And then also we operate that the meteorological satellite monitoring the ocean color and also greenhouse gases. And recently we launched and operate GeoComSat, named the GeoComSat 2A and 2B. One example, there are pictures is for like this, the monitoring the yellow dust, and also this is the surface temperature of the sea around our Korea Peninsula. And also our Korea have launched our KPLO as a lunar orbiter in 2022, and also we will launch our lunar lander in 2032, and also we have a long-term plan as a 2045. Then I'd like to suggest for like a cooperation on Asia climate change monitoring together. So our Korea and India and Japan and China have their orbiting satellites. So it's a cooperation and joint efforts among these Asian countries on climate change is very imperative in these days. So for the cooperation should be started soon. So for further cooperation in detail, I think related committee of India and Korea Academy of Engineering would start their dialogue. Okay. Thanks for your attention and shukriya.
Thank you very much, Dr. Jujin Lee, for that interesting talk. And it was nice to hear from you the global trends in satellite development, then the Earth observation, the clear signals of climate change, and Korea's development in the space sector. So thank you very much once again. So now the two senior leaders have shared their thoughts and vision with us. And certainly cooperative efforts among the countries for climate change monitoring is the need of the hour. And harnessing of new technologies also becomes very important. We need to discover the intrinsic hidden value of the data, which we already have as well. So it has been a very, very interesting keynote session. Thank you once again. This wraps up the keynote address. So now let's move on to the first technical session on the development of core technologies to promote satellite image utilization, co-hosted by session chairs from India and from Korea. There are two talks each in this session by speakers from Korea and India, followed by a question and answer session and wrap up by the session chairs. Now I have the pleasure of introducing the distinguished session chairs from NAEK and INAE. Professor J. Kyo, session chair from NAEK, is the head of the Department of Aerospace Engineering, Seoul National University, and has served as the technical advisor, Space Science Technological Committee of the Ministry of Foreign Affairs. Session chair from INAE, Dr. B.N. Suresh, is Chancellor, Indian Institute of Space Science and Technology, and Honorary Distinguished Professor ISRO. He is also the former president of INAE and has served as the director of Vikram Sarabhai Space Center and is the founder director of the Indian Institute of Space Science and Technology. I now hand over to the session chairs. Thank you.
Thank you. Thank you.
Can I start?
Okay,
Yes,
so
sir.
thank you very much for the warm welcome and warm introduction of the session chair. Thank you very much. So let me thank again our two keynote speakers from India and Korea, both Dr. Nayak and Dr. Lee of both academies. So my name once again is Jake Yo of Seoul National University, and I'll be session chairing two Korean speakers. I think our Indian section, Dr. Suresh will handle those two other Indian presenters. Okay, so I think we are going to go ahead and welcome you to our next speaker, Dr. Taegyun Jeon, CEO and founder of SI Analytics, and he will share us with a space partnership exploring joint satellite applications between Korea and India. Okay, so Dr. Jeon, go ahead when you're ready.
Thank you for the introduction. My name is Taegyun Jeon, and today I'll talk about space partnership between exploring joint satellite application between India and Korea. Before starting our session, I will briefly introduce myself. And my name is Taegyun Jeon, and CEO and founder of SI Analytics. We established our company with the satellite initiative, which is the satellite manufacturer in the South Korea. We especially focus on the geospatial analytics using the satellite imagery and the geospatial data. And I found our company 2018, and we have a strong synergy with the leading space group members, especially satellite initiative groups and the Hanwha Aerospace and Hanwha Systems. And also we globally work with the partnership with the major space company like the Maxar, Planet, and the Black Sky. And we serve the Korean defense and intelligence customers through providing the satellite image analysis platforms. And this is our research result, and we highly recognize of the Earth observation through the artificial intelligence. We mainly focus on the object detection and the segmentation, domain adaptation, and damage assessment and weather predictions. Especially last year, we recognized of the water resource management innovative AI solution under the name of the UNESCO, and we have presentation at the COP28 at the UAE Dubai. So I will briefly introduce our work and what we as target. And also we got a trust through our government, especially the military, and how we adapt the AI capability for the military service or the satellite monitoring. And also we have the strong partnership for the worldwide, especially the satellite image provider and the AI infrastructure and the national security. We globally work with our partners, and we collect the satellite imagery through our satellite image provider and our national satellite. And we combine almost over 300 satellites through electro-optical and the SAR. So we combine under the cloud-based systems. We provide our solution and platform and the service for the worldwide. So especially we highly targeted the next step of the geospatial intelligence. So we collaborate with the US company and the US government. And the right figure shows the former director of the NGA as the fire chat with me. And we discussed about how we can go further through the geospatial and artificial intelligence. And I will briefly introduce our solutions and our target problems. We set up a lot of the Earth observation problems, and we highly focus on the national security and the economy, finance, national disasters, and the climate forecast. This is our model. We have the same Earth, but we have the different perspective. The first priority is the national security. The major using of the satellite imagery is the first priority is always national security. So we provide our capabilities to monitoring for the worldwide or the near countries. But the other side, we have to collaborate with the one entire globe. That means we have to gather the satellite imagery, geospatial data, and the AI capability into one single important problem. So we set up the Earth intelligence, such as the weather, climate, and the national disaster, and environment and energy and food. So this point is what I want to discuss with India and Korea. So we have to collaborate, and we have to collect a lot of the satellite imagery and geospatial data into one entire partnerships, and we have to discuss and we have to research, go further to solve this Earth intelligence problem. This slide shows our fantastic work based on the GeoAI foundation model. We compressed all the Earth observation data into one single foundation model. So we can embed the planetary DNA of the behavior, change, and all the appearance of the Earth through the Earth observation data. So we can expand these foundation models for the various applications, such like geospatial search, change detection, and the downscaling, mapping, detection, whatever. So last year, we promote our large-scale foundation models, and in this figure, a lot of the AI model is based on the language. A lot of company getting much more data and AI capability and grows their scale, how they can understand the human language and how they can interpret and how they can generate the language through the artificial intelligence. So we have a new point. We have almost 2.4 billion size of the foundation models. It is similar with the GPT-2 opened by the OpenAI. So our foundation model is the purely training by the only satellite imagery. And we understand the various appearance of the Earth through the satellite imagery. So we adapt these foundation models for the various key tasks like the detection, segmentation, and the super resolution. So we want and we can collaborate much more satellite data and can adapt a lot of satellite imagery and geospatial data in these foundation models. So I really hope to work with the many countries and many society and many organizations which can contribute the satellite imagery or the geospatial data into one foundation model. This work is very unique and very foundation and can expand the adapt the worldwide country. So I will introduce our platform and solutions. So first of all, I will introduce our Ovision Intelligence. This is the operational ready analysis ready platforms for the defense and the intelligence community. So a lot of features can detect and analyze the Earth observation data. So we can provide a lot of the government and the defense and the intelligence customers. So this slide shows the one application example for our country. So based on a lot of the higher resolution and the low resolutions, we can combine all the data from the satellite to make the much value. So first one is we adapt the super resolution technology and enhance all the countrywide the base map. So we adapt our super resolution product for the planet 3-meter resolution low image. And then we adapt our detection capability for the worldwide. And we found a lot of strategic assets. And dynamically or the repeatedly, we can change. And we found the change of the anomaly detections based on the key technologies. After that, we can provide our commercial capability for the government side. We operate our own commercial satellite AI centers, and we consume from the satellite image provided by the worldwide satellite image provider, and we can distribute and the collecting and the tasking and applying the AI capability for a lot of the government missions. So this is the number 2, the Ovision Earth. To solve the Earth intelligence problems, we collect a lot of the free and the government and the worldwide imagery into one single platforms. This is the web-based platform, and we solve the weather problems and mapping problem in these single platforms. So the next solution is the Super X. Naturally, the satellite imagery comes from the human vision. So we enhance the Earth's clarity, and we can process a lot of and tons of the satellite imagery very short time. And we can cover the daily processing capability. And also we already have proven with the Maxar and the Planet. So we naturally enhance the resolution of the satellite imagery and making clear imagery through the government or the customer and also the image providers. So the resolution of the satellite imagery can be enhanced. And also we got another result from the machine. That means the original imagery can be clearly by the human eye, and also it can be very powerful for the machine eyes. So we enhance the AI capability through the Super X, and as you can be seen this slide, after processing the resolution enhanced, the AI capability can extract much more information through the satellite imagery. And this example shows the work process and highly increased almost over 200%. And the road and the building is the highly extracted through the low resolution imagery. Starting from the plane scope with almost over 3-meter resolutions, and the original satellite imagery cannot be sufficient for the extract the building and road footprint. But after processing the resolution enhancement, so AI can collect much more information from the satellite imagery. And the third thing is I would like to highlight this part. So weather is our powerful climate change prediction solutions. So we focus on starting from the extract the appearance and the movement of the cloud. And then we generate through the Gen AI, and we convert the radio types, the rain predictions. And after that, to combine this cloud movement and the rain, and we can predict of the track of the typhoons. So we mentioned all the people on Earth will be warned in advance to protect themselves through AI and weather satellite data analysis. But as you can be seen in this slide, a lot of the weather radar system can cover the several nations, but the other side, the black and gray scale is not covered by the radar systems. That means that we have data inequity. So that means we have to combine all the satellite imagery for the one single globe. So we combine 3 different geostationary satellite imagery from the US, Europe, and the South Korea. So we connect these 3 geostationary satellite data, and we bring the gap of the climate informations. So after adapting generative AI, and we can predict the movement and the appearance of the typhoon and the cloud. This slide shows the real observation through the GK2 geostationary satellite data and our prediction result. And also we can generate from the geostationary satellite data, and we generate the radar map. And we can cover and we can highlight without any radar system data. So the final result is the correcting and tracking the movement of the typhoon. This is the example of the 2022 Hinnamno cases. in the South Korea. So and last year, the reveal eastern city of the Dharma before the after and the flash flood, and this 3D simulation through the visualizing and the extent of the flood area. So our capability and our mission is the cover and go further through the without the sufficient data. Through the generative AI, we can make and we can create new types of the geospatial data based on the converting previous Earth observation data. So we can predict and we can make the new simulations and new future directions. So we propose the new types of the forecasting through the weather intelligence, through the AI solutions, combined with the typhoon trajectory predictions and the forecasting cloud movement and the rainfall and accumulate the precipitations. So through the whole this process, we can cover and we can provide our weather intelligence with any other region without sufficient data system or the sufficient geospatial data. Yeah. Thank you for listening. This is the end of my presentations. Thank you.
Thank you. Now I think we will proceed with the second lecture in this series that will be given by Nilesh M. Desai, who is the Director of Space Application Center. He has 38 years experience in development of variety of complex payloads catering to different applications involving Earth observation, communication, navigation, and many more. And of course, he has won several awards, and also he has participated in several international committees, organizations. And the topic that he's going to give a lecture is India spaceborne payloads and associate technologies for product generation. Over to you, Dr. Nilesh M. Desai.
Thank you, sir. And let me welcome all the participants and the office bearers of INAE as well as NAEK. And let me thank the organizer.
Yeah, you are audible. Go ahead.
Yeah. So, as the topic says, the current status and cooperation plan of the satellites for observing the Earth. So, under that broad umbrella, today I would like to cover the ISRO India's spaceborne payloads and some of the associated technologies for product generation. So, after listening to Dr. Tegu Jion about his capabilities shown by his company, I would like to now take you through a journey of India's development efforts related to various Earth observation satellites. I'm sharing my presentation. Is it visible, sir?
Yeah, visible. Go ahead.
So thank you. And today is a very historic day. Of course, we are organizing this seminar. That is one part. But in 1964, world's first geosynchronous geostationary satellite, SIMCOM-3, was launched on this particular day. So in that way also, this is a very historic day. And in 1960, we had Sputnik 5 traveling with the live organisms. So that way, today is a very historic day, and on that day, I would like to present my presentation related to various spaceborne payloads developed by ISRO and India and the associated technologies. All of you are very much familiar with India's space program, which has been envisioned by Dr. Vikram Sarabhai, who incidentally belonged to the place where I am sitting right now at Ahmedabad in Western India. And of course, after his premature death, it was steered by Dr. Satish Dhawan and Dr. Kalam Saab. All of you are well aware of that. Professor Yashpal has been the pioneer of various space application activities here at Ahmedabad, center of ISRO, Space Application Center, where I am sitting right now. So, and the motto of our space program is that we want to use space research and technology for the benefit of common man and society. So, following these details, we began our space journey in 60s, and we started with various programs related to rocket development, communication, TV broadcast, all those things. Dr. Sarabhai used to say that if we want to make satellite and various technologies, first we should learn how to use the satellite for various applications. So right from the inception beginning, our program had been user-driven or application-driven. And today there is more emphasis on various user-driven programs or application-driven programs. So we are trying to meet those requirements. And of course, the remote sensing experiment, about which we'll be talking today, about various developments, we started at PRL here at Ahmedabad, where Dr. Pisharoti had an initial program related to coconut experiment related to monitoring the disease from space or from a aircraft platform. So that's how we began our journey related to various remote sensing experiments. And today, day before yesterday, on 16th August, we launched our microsat 2C satellites, and I'm happy to inform the gathering that both the payloads have been switched on and they have started giving initial data related to various Earth observation, electro-optical IR payload, as well as the GNSS reflectometry payload. So in last 55 eventful years, we had around 222 missions, a very satisfactory record as far as ISRO is concerned. And although today there is a lot of hype and euphoria about our space exploration program like Chandrayaan or Mangalyaan and Gaganyaan, about which there has been a lot of talk nowadays, but the basic activities, which almost 75-80% of activities being done by ISRO is related to the applications which concerns the common man in society, and Earth observation is a major element in that. So almost 40% of activity which ISRO does is pertaining to Earth observation, whether it is related to electro-optical payloads or radar technologies. This is the place where I'm sitting right now. That is the Space Application Center, which has been the major torchbearer as far as the development of these Earth observation payloads as well as these applications are concerned. So, in fact, we worked on various communication and navigation payload as well. But today, I'll be more talking about the optical sensors which are being developed by us for Earth observations, as well as the microwave remote sensing activities which are being done here. And apart from payload or sensor development, we also carry out various pilot projects related to applications and then hand it over to the actual users for the commercial as well as the other exploitation of this data. And our institute is more like an academic institute because we have domain knowledge, specific skill development related to various fields, whether it is mechanical, electronics, computer, as well as various science-related activities, which we do it here in view of our applications specific activities. And we work in close collaboration with industries, whether it is small or medium enterprises, various academic institutes, various research institutes, as well as international space agencies. So coming to the remote sensing Earth observation activity, which are being done by us. So it pertains to both optical and microwave, as already mentioned. And in that also, we have both passive as well as active remote sensing activities or payload developments. So covering from DC to GC, as we call it, from very low frequencies to very high frequencies as well, covering IR and electro-optical, various visible near IR and very high-end hyperspectral and various type of imaging. And in microwave also, we carry out activities related to from lowest frequency VHF, UHF onwards up to gigahertz, and now we are moving towards the terahertz technologies as well. So I will take you through a journey of all this payload development which we have carried out during recent years. So starting with our electro-optical remote sensing program. So we have satellites pertaining to both land, water, as well as high-resolution cartography, oceanographic, and meteorological observations. Of course, meteorological and climate-related observations are from geostationary platform, while the other ones are on LEO platforms. And when we started our journey in early 70s, we started with a resolution of hundreds of meters or kilometers. And today we have reached with our Cartosat 3 satellite resolution with up to 0.3 meter, that is equivalent to roughly around 1 feet. So from 1 kilometer to 1 feet, it has been a very enlightening journey all throughout development of these various electro-optical sensors. And now we are planning a geostationary imaging platform as well with our GISAT program. So this is how our electro-optical payloads journey in last 45 years with more than 50 payloads. As I said, we started with few hundreds of meters and now having moved to 1 feet or 0.28 meters, starting with IRS-1A and now moving on to our latest Cartosat 3 series of satellite. And of course, we are waiting for more development related to various applications, whether it is land, water, cartography, for urban mapping, oceanography, and various scientific and planetary exploration. There also we have various high resolution as well as medium resolution camera systems, as well as meteorological and surveillance sensors from geostationary orbit. And of course, we moved from panchromatic stereo imaging to multispectral camera systems, hyperspectral, and now we are moving on to ultraspectral imaging as well. So these are some of the recent developments related to our electro-optical sensors, where one of the big satellites we launched recently last year was OceanSat 3, which contained a ocean color monitor as well as SST monitor payloads. Of course, the SST monitor payload developed some issues. So right now only OCM 3 is operational. And then we have microsat series as well as nanosat series of satellites, which we are launching regularly. And of course, Chandrayaan 2 and Chandrayaan 3 contain very sharp camera systems for various applications related to imaging as well as landing. And Aditya mission also contained Welsi payload, which is again observing the sun from a L1 Lagrange point. As I mentioned, on 16th August recently, 2 days back, we launched this EOS-08 or Microsat 2C satellite, which contained a very innovative electro-optical IR payload. And this is the first time such a high-resolution camera system in IR it will be available with a 5 kilometer swath from a orbit of around 450 kilometers. So it will be very useful for various forest fire as well as weather applications related to LST as well as agriculture residue burning, which is a burning problem here in India. So various themes it will cover. So the users are very actively looking forward to this particular payload. We have started initial operation related to the payload, and shortly we'll operationalize it. These are some of the typical images from starting from high resolution images to nanosat satellite images. This particular bottom, you are seeing a image taken from our Bhutan satellite, which we have launched specifically to cater to the requirements of our neighboring country, Bhutan. And similarly, we have various other applications, whether it is related to high resolution as well as medium resolution mapping for various oceanographic as well as many other applications using this optical technology. And now we are moving on to hyperspectral technology. Of course, we had earlier launched HISIS satellite with a 30-meter resolution and 10 nanometer spectral resolution, 30-meter spatial and 10 nanometers spectral. But the requirement of the user is they demand almost up to 10 to 20 meters out of resolution. So we are now trying to cater to this new generation hyperspectral imaging, and of course our fourth generation Metrosat satellite also we are working on various development related to weather applications. Of course, we have, as far as all these were passive optical remote sensing, and now we have a initiated initial technology development program related to our active optical remote sensing with LIDAR related development. So we have started developing various LIDAR detector development as well as flash lidar and 3D imaging, time of flight lidar as well as FMCW lidar. And right now we are testing this lidar technology with airborne and drone platforms. And shortly we'll be moving on to spaceborne platforms. So this is, we have a good plans for this lidar related active optical remote sensing, and under that we also have this Dyson spectrometer. So till now we had been using the other type of spectrometers, but now we are moving on to zinc selenide Dyson lenses. So that initial development, technology development related to Dyson spectrometer also are ongoing at our place, as well as the neuromorphic camera systems where you can detect the change. So you try to image only the changes rather than imaging the total scenario. So that event-based camera systems also are under development, and especially it will have a lot of applications from geo platform with the lightning mapper, which we are planning for our INSAT 4th generation of satellites. These meteorological satellites, right now, recently in February, we launched our INSAT 3DS geostationary meteosat satellite for meteorological applications. And now we are in the definition stage of our 4th generation satellite, which will be something similar to Himawari and that sort of meteorological observation, which are right now being obtained using advanced imager as well as sounder. So we'll be having a very 16-band advanced imager along with a lightning mapper, which is a major requirement for a country like India, as well as a very innovative hyperspectral infrared sounder. And of course, we have various MET observation payloads, whether it is millimeter wave temperature as well as humidity sounder. I'll show you some of the details related to that, and radiometers from a LEO platform. So combination of LEO and GEO will take care of our requirement for meteorological observation. And during the last year's presidency of India for the G20 group, our Honorable Prime Minister has proposed the development of a G20 satellite, where all the G20 countries will contribute in some way or the other with payload and other developments. So under that, we have defined now a G20 satellite, which India will be offering to all the G20 members for environment and climate change observations. So we have already worked out 4 sensors. 3 of them are, electro-optical region for aerosol and cloud studies. So, and of course, the environmental gas related observations as well as climate studies for forest fire. So these are all the major sensors which have been already defined by us. And now moving on to, this was regarding our electro-optical remote sensing program. And we also have a very thriving microwave remote sensing program. Of course, all of you are well aware that microwave offers a distinct advantage over some of the applications where we can have a all-weather day-night capability with the microwave radar systems. And we have both active as well as passive sensors as far as microwave remote sensing is concerned. So we have passive radiometers and sounders, whether it is temperature or humidity sounder, as well as active radar system. We started initially with the airborne, side-looking airborne radar in X and C band, and then slowly graduated to synthetic aperture radar. And we have now a very thriving microwave remote sensing program with a plethora of active sensors like SAR, scatterometer, altimeter, as well as other wind profiler and other ground-based radars as well. And of course, with this EOS 08 mission, which we launched on 16th August, we have now initiated GNSS reflectometry related observation as well. So these are signals of opportunity available through the navigation signals. So that activity also, and we had earlier Arrow payload with in synergy with the Italian Space Agency earlier. And now we are moving on to quantum radar as well. So if you see our microwave remote sensing program, it almost started with our optical remote sensing program in late 70s. But of course, we took our own time in graduating to developing our own indigenous active radar system with scatterometer on OceanSat 2 in 2009, and then moving on to RISAT, that is the radar imaging satellite with a synthetic aperture radar in C-band in 2012. And after that, we initiated the collaborative activity for a NASA ISRO synthetic aperture radar sweep SAR mission. So here also the resolutions as far as the images are concerned. We moved from few hundreds of meters to again a 0.3 meter sort of or 1 feet sort of resolution with our RISAT-2B, where we have a constellation of 3 satellites taking care of various commercial as well as strategic requirement of the country. So this is how our program, and we have the other unique activity which we have carried out with it. We have synthetic aperture radars in almost all frequency band you can think of, whether it is C band, L and S band, X band, both airborne as well as spaceborne radar. So that way we have a very thriving radar program, and today we proudly say that we have indigenous capability of developing radar which are state of the art. So this is just a typical example of RISAT-1A, which we launched 2 years back on 14 February 2022. And it is being widely used for various agriculture, forestry, environment monitoring, as well as many of the strategic requirement as well. And it has a full polarimetric mode. Unlike our first satellite, RISAT-1, which has a hybrid polarimetry mode, here we have full polarimetry mode. So these are some of the capabilities which show the whether it is tracking of ships in Antarctica or urban mapping of the urban areas like various cities, as well as volcano-related observations. So it has very wide range of application, especially with C-band. And of course, X-band has a very strategic application. Of course, on Chandrayaan-2, we had for the first time, a dual frequency SAR, which gave us a full polarimetric SAR for lunar imaging. So that is also, it has shown very good results, especially related to some of the observation which corroborate with the observation made by M-Cube and other sensors related to the availability of hydroxyl molecule onto the moon surface. So that has again fed into advanced research activity related to that. So this is our development related to lunar imaging. Of course, now we are working on very high resolution radar imaging as well as maritime domain awareness, because that is going to be another area where a lot of strategic interests are also building. And this is the collaborative mission which we have initiated with NASA JPL team and ISRO and Space Application Center. So we have developed a S-band sweep SAR here at Ahmedabad, as well as JPL has developed the L-band sweep SAR, and both the radars have been integrated at JPL, and after test and evaluation, it has been brought back to Bangalore, where it is getting integrated with our satellite. And shortly we are going to launch this in a couple of months. And the whole world is looking forward to the launch of this particular NISR, NASA ISRO Synthetic Aperture Radar, which will open up new vistas of application, especially related to polarimetric and interferometric SAR observations. And of course, land deformation study will feed into the future studies related to detection of earthquake, which is right now a very topic which is under consideration by various scientists. Of course, apart from spaceborne radars, we started initially with the C-band airborne radar for disaster management. And so we had used it for various disaster management activities. So we had a C-band airborne radar, then we have a miniaturized X-band radar weighing around 6 kg, which is easily transportable, and we are reducing and doing further miniaturization to make it amenable for drone-based applications. So similarly, we as a precursor to NISR mission, we had developed this L and S band airborne radar, which was flown very heavily in the USA as well as in India and collected a lot of data. So that worked as a precursor for various application studies by scientists from both the countries. So this is another activity. And now we are working on a P-band airborne radar, which has many applications, especially for subsurface imaging. And right now it is undergoing trials near Hyderabad for collecting data related to foliage penetration as well as forestry related applications. So it is in P-band, and this is precursor to our future spaceborne radar. And all of us are eagerly looking forward to biomass from European Space Agency. Something similar is India is also planning to have its own system. And apart from that, we do a lot of other technology developments related to high resolution wide swath imaging, because there are conflicting requirement of both high resolution as well as wider swath, which is, as all of you are well aware, it is a trade-off. Either you get good resolution or you get better swath. But there are now new techniques. Of course, SweepSAR is one of them, which we have implemented in NISAR. Then there is MIMO-SAR, then frequency scanning SAR, and display space center-based antenna SAR, which with all these technologies we are working on to develop a SAR which will have both good resolution as well as wider swath. We have a very thriving program related to wind observation, especially wind vector observation in oceans. So we have wind scatterometers, starting with the KU band scatterometer, which we developed for OceanSat 2. And then onwards, we built many scatterometers, and India is the only country which has this scanning type of KU band scatterometer, which is being widely used by various meteorological and oceanographic agencies like NOAA, UMETSAT, and all the people around the world. So it is very popular as far as this particular scatterometer is concerned. So right now, one of them is flying in OceanSat 3, and we already have planned to develop the follow-on mission of OceanSat 3A. And of course, we have our own SCATSAT program as well. And future, we are planning to have a dual frequency scatterometer, both KU and Ka, as well as C and KU. So this is typical results obtained from spectrometer sensors, which are regularly being utilized for various wind vector related as well as cyclone monitoring or cyclogenesis experiments, which are being carried out. Of course, historical moon landing by our Chandrayaan 3, it contained a Ka-band radar altimeter, which was a pivotal instrument in enabling the very safe landing or soft landing of our lander, and it played a major role as far as the landing is concerned. So that technology also has been developed, and now we are moving on to millimeter wave and sub-millimeter wave technology with temperature and humidity sounder related developments. So already these models have been developed, and as I said, last year we flew this US-7 mission, Microsat 2B, where we had a millimeter wave humidity sounder on board that, and which has been widely used, and the data has been assimilated into the numerical weather prediction model as well. So this has been a very good achievement, and now we are going ahead with a full-fledged temperature and humidity sounding mission for our meteorological observation. Of course, with the recent launch of EOS-08 Microsat 2C, first time we are experimenting with GNSS remote sensing payload like Cygnus or Gyros and TechThermoset, which has been well established, and now India is moving on to this GNSS reflectometry domain, where the opportunity signals will be utilized for development and for remote sensing. So this is new era of research, and we are firmly into that. And of course, now we are moving on to millimeter wave observation, both from ground as well as in future from space. So we have this cold cosmos or interstellar dust related observations. So we have done initial development of 230 and 340 gigahertz front-end electronics using millimeter wave technology for our various observations before moving on to terahertz technology. And there are plans to build a first sub-millimeter observatory at Henley in Leh. And this is the telescope which we are building with a 66 petal antenna with the initially with 340 gigahertz and then followed by terahertz technology. Of course, cryogenic cooling systems, wideband spectrometer, sub-millimeter wave telescope, and the antenna, which is a 6-meter diameter antenna. So these are all the various front-end technology. And of course, the millimeter wave RF front-end is going to be a real challenge with a Schottky barrier diode or SIS junction type of mixers and other development. So we are on to that. And of course, as I mentioned, for G20 satellite, apart from the 3 optical sensors, we also have a hyperspectral millimeter wave sounder, where instead of having 6 or 10 channels like our normal 183 gigahertz humidity sounder, which we launched on US-07, we will have a 100 channel hyperspectral sounder. So this will add into the meteorological observations, and we are eagerly looking forward to them. As far as the new technology development, we have this quantum radar related developments. Of course, we are working on quantum key distribution for our quantum communication program. As a byproduct of that, we have initiated a precursor development related to quantum radar, which will help us in detecting stealth target as well. So some of the technology development related to that have been initiated. I'll just show you some of the results. This is for typical tsunami observations. So post tsunami damage assessment, mapping of Himalayas using our radar imaging satellite. This is a high resolution mapping of airports. various earth observation application in almost all the domains, whether it is agriculture, forestry, environment monitoring, oceanography, cyclone tracking, everything we are doing with our own indigenous sensors, and this has helped us to reduce the human casualties, as all of you know. And of course, cyclogenesis is being carried out with our scatterometer sensor, followed by the INSAT 3D series of satellite, which tracks the cyclone toward before the final landfall. And as far as product generation is concerned, so we had been following the traditional data processing chain, where the raw data is being utilized to generate various data products, and from that deriving the information products. And the trend now towards direct information product from satellite and analysis ready data. So that development also are being carried out by us. And now the trend is more towards AI ready data. That is, the data is amenable for applying the artificial intelligence or machine learning algorithms. So we are moving on to the AI domain with the various geomatics and geoinformatics applications, whether it is AI, ML, cloud computing, or geospatial mashups, or big data analytics, as well as AR, VR, and other activities. We have developed this global solar calculator using the installation products of our meteorological observations. We have a geospatial energy map of India being developed by our team, which caters to the overall energy sources from various ministries of the country and at one location. And now we are developing the Agri DSS, the Krishi DSS decision support system, which will help the planners and the government officers in working out various aspects related to agriculture, whether it is insurance claims or monitoring the crop growth and many other things, especially during the Kharif season. So all this information available from various sources as well as satellite remote sensing will be available at a single point on a website. We are also working with under the Quad program with the USA, Australia, as well as Japan, working on helping the small developing island states, SDIS activities. So various applications related to cyclone monitoring, storm surge, swell, PFZ, potential fishing zone, flooding, and all these energy sources, all these activities. And so we have adopted right now, started with Maldives and now working on Mauritius for helping them for all these various applications. Of course, under NASA, ISRO, sir, as I mentioned, ecosystem related studies and especially land deformation studies will go a long way in working out a precursor system for prediction of earthquake, cryosphere studies, or disaster management and various geological applications. So, as I mentioned, the whole world is looking forward to the launch of this LNSMSR, and we are now working also on a joint mission with CNES, French Space Agency, and ISRO, working on a Trishna mission where thermal infrared imaging satellite. So thermal infrared payload is being provided by our French team, and ISRO will be providing the visible and IR payloads for this particular mission. So together it will fill in the observational gaps, which is right now for LST, SST, and various applications. Till 2028, we don't have anything in sight. So this particular mission by 2026 will fill into the requirements. We have these three major sites, Bhuvan, Bunidhi, as well as Vedas and Mosdek at Ahmedabad. So they provide various applications related to land, meteorological, oceanographic, as well as geospatial data services. So data with the new data policy 2023, up to 5-meter data is freely available for the users and researchers. And of course, there are price data as well. These are the Mosdek and the Vedas site of ISRO Ahmedabad. So I invite all of you to look forward to that. And some of the activity which we do for using artificial intelligence for VO data processing, data acquisition, data processing, as well as information extraction. So that activity also we are doing along with external areas. So whether it is onboard data assimilation by onboard cloud detection and then transmitting only the relevant data instead of transmitting blindly all the data. Many of these, which is cloud cover, is there, so that we can eliminate onboard itself and have a very meaningful transmission. Similarly, autonomous payload operation is another area where we are working using this AI intelligence. And of course, on ground, we have various applications of AI techniques in remote sensing, image analysis, whether it is related to image restoration, super resolution, where we can improve the resolution by a factor of around 1.4 to 1.5. Image synthesis, where if some of the band data, if it is missing, we can recreate that using AI techniques image segmentation, scene modeling, or understanding or deriving information out of the scene, image synthesis. This is a typical application we carried out for our Carto 3. One of the camera band was not giving the data, so we recreated that using the data from the MX as well as the other bands, image enhancement and improvement using super resolution and other enhancement techniques. This particular crater map generation for our lunar mission also utilized the AI techniques, and of course various application related to urban mapping, renewable energy, vegetation monitoring, or snow cover monitoring. So these we are regularly doing various activity, whether it is related to the 100 smart cities program in India for these using AI for future extraction, as well as this 3D city model generation and volumetric change analysis, crop acreage estimation. These are, we have a AI model as well as a semi-physical model as well. So if we compare the data results available from both these, smart city is one of the major area where solar, rooftop solar energy potential as well as various solar farm related activities are being done. Of course, snow cover and road blockage mapping in Himalayas. So that is a major activity. And then weather forecasting, where we have demonstrated this AI/ML suitability for nowcasting over our Bihar region, which is prone to floods as well. And precipitation nowcasting is another area where we are utilizing AI/ML in a big way. So to summarize, we have a lot of potential working here at SAC as well as ISRO related to remote sensing, navigation, communication, and various science exploration missions. Today we have covered this Earth observation related activities being done by us for India's space program. So, thank you all for patiently listening. I thank INAE and NAEK as well as all the session chairs and keynote speakers for giving me this opportunity. Thank you, sir.
Thank you, Dr. Nilesh Desai. It has been a very, very comprehensive spaceborne payloads and associated technologies, detailed presentation. And stay back, I think the question and answer is only after the 2 more lectures. So please stay back.
Okay.
I think there will be a couple of questions. Now I hand over to my co-chair, Dr. Jayashik Yof, for
Okay.
the next lecture.
Thank you very much. Once again, thanks, Dr. Desai, for giving us a comprehensive view what is happening in your Space Application Center in Ahmedabad, right? Okay, so thank you very much. So it is time to go ahead with our second speaker from Korea, and it's Dr. Youngjae Park. He is currently a Chief Research Officer of Telepix. And he'll give us a talk on leveraging high-resolution optical imagery to address coastal water issues. Okay, so Dr. Park, when you're ready, please go ahead.
Thank you very much, Chairman. Yeah. Can you see my slide?
Yeah, go ahead.
Yeah. Okay. Okay. Good morning or good afternoon, everyone in India and here in Korea. My name is.
Can you make it full screen? Can you make it full screen if you can?
All right. Sorry. Yeah. Well, I forgot it.
Yeah,
Thank
okay.
you. So my name is Youngjae Park. I'm currently working with a Telepix company, a space startup based in Seoul. I'm truly honored to have this opportunity to present my research in this excellent workshop. My presentation is about leveraging high spatial resolution optical imagery to address coastal water issues. Before going into the main topic, I would like to briefly introduce the business area of our company, Telepix. Telepix products can be broadly categorized into 2 main areas. The first category includes payload, particularly suitable for small satellite platforms such as CubeSat, which including our high-performance DMA camera, as you see on the left lower panel. The second category consists of solutions for analyze and servicing satellite data observed from our own or third-party satellite. Telepix is looking for synergy by simultaneously advancing both hardware and software compartment. Now, moving on to today's main topic, there are several coastal water issues where satellite-based monitoring can provide significant benefit. Traditionally, this includes health and water quality, but recently, floating algae and floating marine debris have also attracted attention. Monitoring these coastal water issues has been challenging until recently. This is because ocean observation sensors typically offer spatial resolution of 1 kilometer or a few, for few band, 250 meters, which is absolutely insufficient for observing areas near the land. On the other hand, terrestrial observation satellites like the older Landsat series either lacked the necessary band or had insufficient signal-to-noise ratio. Additionally, there were often issues with insufficient observation frequency or low reliability of processing results. As shown in the next slide, the performance of satellite sensors has significantly improved recently, leading to increased expectation for the role of satellite remote sensing in monitoring coastal water issues. Now, this slide shows from left to right the Korea's geostationary satellite GK2B and the United States Landsat 8 and Europe's Sentinel-2 and the commercial CubeSat satellite SuperDove on the right. Boshi-2 onboard GK2B is the first kind of its kind of satellite to provide multiple daily ocean color observations, while the Landsat 8 or Sentinel-2 offer high-quality imagery over the coastal waters, making significant contributions to addressing coastal water issues. What's remarkable is that the data from the CubeSat, like SuperDove, which is dimensions only 1/5 the size, and the weight is just 1/200 or 1/500 that of traditional large satellite, is currently widely used. Particularly, the ability to operate a large constellation of these CubeSat satellites and observe the entire globe once a day is a very significant advantage for monitoring rapidly changing ocean environment. This slide shows I showed a couple of graphs. So this slide shows the gray line representing the atmospheric transmittance due to atmospheric gases, indicating the strong absorption in 760 nanometer, and also the strong water absorption in this NIR band. And the colored line represents the spectral response functions, in this case, Cauchy-2. And Cauchy-2 has a 12 spectral narrow band with GSD 250 nanometer. It provides 10 times a day without cost. And the next Landsat 8 OLI sensor has 5 band in the visible NIL region, in addition to SOAR and TIL bands, which is not shown in this graph, and provide images with 30 meter GSD every some 16 days. I'm not sure it's 16 or 15 days. And the next one is the Sentinel-2 MSI sensor, has 3 additional bands in 700 to 800 nanometer spectral range here. And the one additional band around 950 nanometer compared to previous OLI, including the SOAR bands. And sorry. And the top is PS2, which is the 8 spectral bands in the visible NIL atmospheric transmission window, except near 760 nanometer and 800 nanometer. Through constellation operation, it provides images with 3 or 4 meter GSD, approximately every 2 days currently. For coastal water applications, the NIR and radiation bands are sometimes extremely important. Sentinel-2 has 4 such bands. Bush-2 has 3 bands, but the Superdove has only 2, and the Landsat 8 has only 1, which could limit the algorithm development. And yes. And now I'll take a look at the harmful algae bloom in the next couple of slides. In Korea, harmful algae bloom, also we call it red tide, is a recurring problem that causes massive mortality of aquaculture fish. As shown in the table, there has been large and small scale HAB events from 1995 to 2020. And in Korea, 60 HAB species were reported. But the most prominent one is Coclydinium, as you see on the lower left. And the second one followed by Karenia in here. So according to the red tide report by NIFS, the National Institute of Fisheries Science in Korean, which is based on field survey, the area where red tide were observed in 2022 is highlighted in the red pixels in the central part of southern coast of South Korea. And starting from the area, the marking in this the border sea in the orange area, the red tide can expand to cover broader area, actually further to the west and further to the east, covering up to 200 kilometers east to west, indicating that there is a strong need for wide area monitoring for red tide. And as the term red color suggests, HAB changes the color of seawater. So this discoloration should be visible in the color composite image. So this slide shows the GOSI-2 RGB image of the level 1B TOA reflectance for 3 dates. So it's before the red tide on July 19th, and during the bloom on 7 September 22, and end of the bloom in 23 of September 23rd. Within the red oval in the medium middle image, we clearly see that some reddish dark pixel which indicate the bloom of red tide. And the next slide shows the same color composite, but for the water reflectance, which is obtained after atmospheric scattering effect removed. In the central image, you can, the color change in the red area is more clearly visible after atmospheric correction, and it can be inferred that the red is likely to happen in the nearby area as well. So up to now, we have qualitatively estimated they have occurrence based on the color variation, but we need an algorithm for quantitative analysis. In fact, many rate-tied algorithms have been proposed by numerous researchers for application to various satellite imagery. But I'll skip over those details, but briefly, the algorithm discussed here is compute reflectance height at two bands, 680 nanometer and 705 nanometer from the baseline, utilizing the strong red absorption of phytoplankton species that cause harmful algae bloom. We called it the reflectance height, red tide height, or H underscore RE. The advantage of the algorithm, the simple the reflectance height algorithm, is that it can apply to either TOA reflectance or water leaving reflectance after atmospheric correction. If the atmospheric correction is feasible, such as with GOSI-2, the method, the one, involves the calculating HRA from directly from the atmospheric corrected raw RRS, which may be more correct than the method 2. The method 2 can be applied where the atmospheric correction is not feasible. This is often it is difficult to atmospheric correction for high resolution imagery, such as Sentinel-2 or MSI. So now the method 1, we apply GOSI-2, and method 2, I'll apply to MSI. And to compare the images from GOSI-2 and PS Superdo, we used the image taken on September 7th, where the rise tide occurs. And let's investigate area 1 and area 2, which is in close area, which appear similar in color in this RGB composite. And for the area 1, please, for area 1, GOSI-2 image is shown in the top left, and the HRE result from the algorithm analysis is just below it. And while the colors of point 1 and 3 here is very similar, but only if you look at the spectra, only the series 1, point 1 shows the signature of red tide. So in the PS image, if we look at, we have very the detailed the image of red tide in this area, and if we look at the area, the point 1, 2, 3, we confirm that only series 1, point 1 has red tide, which is enhanced reflectors in this red edge band, but the other two doesn't show do not show such spectral signature. So the GOSI-2 and the PS provide consistent result. And now for area 2, where you are looking at the image from the GOSI-2 RGB image, and the below it you see the red tide analysis output, and PS image RGB image shows like that. If you look at the spectra in this area, it doesn't show any spectral indication for red tide. So in this case, too, we see there is consistency between GOSI-2 and PS. And moving on to the next slide, to compare the Goshi-2 and Sentinel-2 MSI image, we used the images on September 9th, 2 days later. And on the left, the NIFS red tide report show rare occurrence of red tide. However, in the Goshi-2 image, the dark reddish patches in the middle image are associated to the positive value in the HRE image on the right. So suggesting that the red tide has spread widely in this area. But we see the in situ observation is very scarce. And the Sentinel-2 MSI derived the red tide strength, HRE. The image shows that the color composite and the HRE on the right. And while we see that again the same point 1 to 3, looking at the point 1 to 3, the point 1 and point 3 both displayed red tide the features. In this case, if we look at the around 700 nanometer, we see, but point 2 and point 4 is in this area, do not show any red tide. So notably, when we comparing 2 days earlier image, the point 1 has changed from non-tide to red tide pixel in this case. And the next slide, I want to compare the Goshi-2 and MSI. If you look at both images, the general pattern generally quite similar, but there are some observations in the Goshi-2 image which detect as red tide, but in the MSI, they don't. So which, of course, in this area, the red tide is detected very weakly in blue signal, but which means very weak. But in this case, obviously it's the false alarm. So which require further investigation. So this concludes the section on red tide detection. Now I would like to discuss on marine floating debris. Specifically, I want to examine 2 events. In the very large-scale floating debris event from the March 21 East Japan tsunami, and secondly, the debris caused by heavy rainfall in the southern Korea in 2018. I want to skip the third one due to the time limitation. So on 10 March 2011, one of the most powerful earthquakes in the world since modern record keeping began in 1900 occurred offshore of the east coast of Japan. And the quake triggered powerful tsunami waves 3-meter height, reaching up to 10 kilometers inland. And the tsunami caused the Fukushima Daiichi nuclear disaster. And many towns along the Japan coast, East Japan coast, are devastated, as you see on the photo, right? And this figure is from Matthew et al. In 2017 paper. They shows a rapid eye 5-meter pixel size image clearly shows the floating debris in the RGB image. You can see these patches. near the Fukushima Daiichi and Daini nuclear plants, which is observed on 12 March, just one day after the earthquake. I was wondering if we can see such a great-scale marine debris event in the 500-meter Goshi 1 image. Goshi 1 image is 1 pixel size of 500 meter, which is 100 times bigger than rapid eye pixel size. So to compare the image, the rapid eye image a little bit sized and slightly rotated, and the Goshi RGB composite image on the left side, and the debris analysis result show distribution is shown on the right. Basically, even if the 500-meter pixel it captures the general pattern of the floating debris, it is quite amazing. So even in 5-meter resolution image, the overall distribution is clearly visible and quite consistent with the 5-pixel imaging. So this slide shows the distribution of floating debris 1 day, 2 days, and 7 days after the tsunami from left to right. As time passes, you can see the floating debris a little bit moving offshore as time goes. On the second image, which is a very clear day of the 13th, the result shows the debris observed over the wide area along the coast, extending from the very north to the south, to the south. So the extension of the floating debris is more than generally anticipated. And now from the analyzing the debris pixels, we can get the basic idea of floating debris detection. So the principle of the detecting floating marine debris on the seawater is based on the reflectance characteristic that differ from seawater itself. The graph on the left shows the spatial anomaly reflectance from randomly chosen debris pixels. And the spatial anomaly reflectance, which is defined as the reflectance from floating debris pixel minus the surrounding seawater reflectance. The spectrum the spectrum of the floating debris shows an increasing in reflectance, the increasing wavelengths, which is also reported in other independent studies. I'm skipped one. And next, let's examine the occurrence of marine debris, much smaller scale, but it is quite large scale in general in locals in Korea. So the marine debris caused by heavy rains in August 2020 in Seomjin River catchment area in southern Korea. The traditional market village known as Hwage Jang터, means Hwage marketplace, was almost completely inundated, as you see on the left image, or left photo. This heavy rainfall caused flooding in southern central region of Korea, leading to a large amount of land origin debris being washed into the sea. And this Seomjin area is located here, and we see the more detail in the next slide. So in the MSI image, the red rectangle on the map, in this row left RGB image corresponds this small red area. And the image obtained on August 17, 10 days after the heavy rainfall, and the floating debris is not clearly seen, visible in the RGB image on the left. But after applying the algorithm, it is definitely detected on the result, as you see on the right. So the another MSI image, but is not the same area, but slightly on the left part. You can. This is from the August 20th, 3 weeks after the rainfall. Higher, we see a very higher concentration of floating debris was observed over a wide area within the red rectangle area. So, and also we have the same day, the 20 August of 2020, we have a Lancet OLI image where we took the small area, this small red rectangle area. It is difficult to see from the RGB image, but after applying the algorithm, we can clearly see there was a spread of marine floating debris. So again, on the previous 17th of August, we in addition to the previously mentioned MSI image, we have PS2 image was acquired and analyzed. Although the image is noise, a little bit noise, the presence of floating debris can be confirmed, as you see on the bottom image. So now, when I want to compare this MSI 20-meter data and PS2 3-meter GSD or 4-meter GSD, and obtained on August 17th, and as I expected the PS2 image, if you look at a little bit detail on the right side, we can see some more detail of the floating debris. However, it is noted that PS2 image is quite noisier than the MSI 20. So when we compare the MSI and OLI 30-meter right image, which is obtained August 20, 2020, similar patterns are observed within the commonly observed area indicated by the red circle. But if you look at very carefully, there are subtle difference in detection result, which might be due to the image quality, such as sun glint. I'll not explain the details. And so this is the final slide. I think the least advanced in satellite technology are enhancing the coastal water monitoring for HAB, floating algae, debris, and more. And as a multi-satellite monitoring strategy, we can use Gaussian image at 250-meter resolution, MSI and OLI, something weekly images at 10 or 30 resolution for routine monitoring. And if there is something happening, then we can use the commercially available PS image, high resolution data for target monitoring. And although we have a lot of challenges for addressing the coastal water problems, I'm very sure the multi-satellite application, especially higher spatial resolution imagery for coastal waters, will continue to increase as satellite technology advances. Thank you very much for your attention.
Okay, Dr. Suresh, are you ready to introduce our Indian section presenter?
Thank you very much for the nice presentation, and we are moving to the final talk. Mr. Soya Singh, is he available there?
I'm here.
Yeah. Okay. This is the last talk. In fact, he's the CEO and co-founder of Galaxy Space. They are involved in building a constellation of SAR and Earth observation, miniaturized spacecraft for providing unparalleled imagery to users, actually. And he, in his biodata, interestingly mentions that he had the opportunity to meet Elon Musk because he participated in the competitions organized by the Elon Musk group, that is Aviskar Hyperloop. And I think this group, headed by Soya Singh, they built India's first ever proto of the Aviskar Hyperloop, and then became the finalists. It's very interesting. And I think they stood 21 in the series of 2,500 global applicants. The talk that he's going to present today is bringing consistency in satellite imaging world through Drishti satellite. It's a multi-sensor satellite. And over to you, Soya Singh.
Thank you so much for giving the opportunity to talk, and thanks to INAA and NAEK team as well for organizing this. Today I'm going to keep this entire presentation a little more brief, and that's where I'm going to start the entire talk. So as Sir already mentioned the topic. I'm going to discuss about a particular thought process that led Galaxy to exist, right? And which is basically bringing consistency to satellite imagery through Drishti or multi-sensor satellite. I think I keenly listened to all the three lectures ahead of me, and it pretty much kind of covered the entire spectrum of what satellite imagery or Earth observation can do. Right now, we at Galaxy are not trying to really go in any of the spectrum. I think they already exist. We have found one small gap in this entire industry, right? So when I was going through, when Nilesh sir was talking about all the efforts made by ISRO, I think it's one of the massive things that we are really proud of. Here we are talking about one small gap in this entire imagery world, which we are trying to fix at Galaxy, and hence that will open up a big market. Now, before jumping onto that, I'm going to introduce my team, right, and also tell about briefly what we have done in the past. So, my team consists of 5 founding members. We all come from IIT Madras. It starts with Rakshit. Rakshit is the lead of the product, and he comes from a background of computer vision, worked with Siemens earlier. I am Suyash, and I'm the co-founder and CEO of Galaxy. I have some background in satellite imagery earlier. I worked in a corporate where I used to do forest fire analysis using satellite imagery. Then we have Daniel Chavda, who is the co-founder and CTO. He works into the radar systems, or effectively synthetic aperture radar. Then we have Kishan Thakkar and Pranit Mehta, who are also the co-founders of Galaxy and also leading the engineering and sales and BD efforts. So, we all 5 come from IIT Madras. We have worked together there. And a brief history, as Suresh sir also mentioned while introducing us, we met Mr. Elon Musk. So here is a picture of, where we hanging around with him at SpaceX headquarters. And, we were building Hyperloop pod, and we were actually running it there. It was one of a great experience wherein we were able to understand the different cultures from different parts of the world coming together and building a particular deep tech project and executing it. Now, this project not just was Hyperloop, but also for us was an entry towards space because we were inside SpaceX. We kind of understood how they are building, their own launch vehicles in such a small space. What are they really doing in a private setting there? And that got us to really move forward one step and try and solve a bunch of other problems that we can. And hence, after our SpaceX journey, we came back to India, and we saw that satellite imagery is witnessing a lot of widespread commercial adoption, like as opposed to strategic adoption, which was already there. And we found that it is across spectrum, it is across applications and domains. You can take agriculture monitoring, you can take maritime, which is dark ship monitoring, you can take carbon auditing by carbon traders, and a lot of things are there. Although, when we started to build some of the applications ourselves, what we found that there are two primary data sources amongst many, which are generally used and are available today for imagery intelligence. If you take these two class of sensors, one is optical or hyperspectral or multispectral imagery, wherein it's a great imagery because it's rich in information. You can pretty much find out everything there. Some of the companies who are here are Planet and Pixel, who are working on the optical and hyperspectral side of the story. Then you will find some people in SAR, like ISI, Capella Space. Of course, ISRO has already proven both the class of sensors that are there, right? So we have RISAT and Cartosat already imaging Earth on a consistent basis. What we found that on one hand, which is optical and hyperspectral, you have a day imagery, although when it is cloudy or night, your availability is pretty low or on the lower end. While on the SAR image, the availability is pretty high. You have an image every time, be it a cloudy day or a nighttime imaging, a night time as well. But it's not very easy to understand by a common developer in the commercial domain. You really need to understand the science behind SAR to really exploit it and do something about it. So these are the two classes of imagery. Now, any single sensor imagery data generally is not enough and is not enough to do any use case analysis. You generally need a multispectral or a SAR to come together for many of the applications that are being used today. And it is because of the inconsistent data acquisition nature of it. For example, you may have a good or a non-cloudy situation today, but for, let's say, next two captures, you will have a partial cloud cover of 20%, and then you may have a full cloud cover of 100%, and you may not get the right image for your analysis, right? So imagine you building a SaaS application, which is software as a service, to monitor a particular crop every 7 days, and you have one imagery today, which has no clouds. So you're able to analyze that today. But for next three, imagery collection, effectively your software as a service application fails because it doesn't know how to analyze a partial cloud covered image or a fully cloud covered image. Okay? So now, the answer is you really need to do fusion of data sets, because when you do fusion, you will have enough understanding about that particular scenario. Even if it's a crop monitoring situation or any other situations, fusion in most of the use cases becomes prominent. While, doing fusion today is challenging, and it is challenging because the data is acquired independently. It is acquired from two different satellites, which basically are not temporally matched. Right? Something is probably acquired at 10:30 a.m. in the morning by an optical or multispectral satellite, and with a SAR satellite, it'll come at a different time, which is, let's say, 6 p.m. or 7 p.m. in the evening. So temporally, it is not matched. Spatially, which is basically the resolutions of the two satellites will also not match. And perspective, so one multispectral, of course, is at nadir, and synthetic aperture radar is off nadir. So your perspectives also don't match. So data fusion becomes extremely challenging because A, you don't have a temporal match, B, your resolutions also differ, and C, your perspectives because of at nadir, off nadir situations also differ. And hence, data fusion for a developer, who's trying to use a satellite imagery today in his laptop or in her laptop, they're generally not very much successful to do data fusion and build applications on top of it. And this basically kinds of creates a bunch of problems, right? So let me take some cases. For example, if you're doing a maritime monitoring, and if you want to do tip and queue, it takes more than 8 to 12 hours to investigate after a tip is formed, right? So because you need to do tipping with SAR and then you finally do a queuing with optical, right? So in some scenarios, tip and queue takes a little more longer. Rapid damage assessment in a natural catastrophe events may also take some time because during a natural catastrophe, clouds are predominant in those areas, right? So to get a real uh, good multispectral or an optical imagery of the location or the latitude longitude, it may take up to 2 weeks to really get an imagery and quantify the losses there. Let's take shrimp culture monitoring, right? Agriculture is definitely something which is very known, but let's just take shrimp culture monitoring for a moment. Diseases are very detrimental to shrimp ponds and can destroy the entire harvest in 1 week, right? So if diseases occur. So imagery obtained between two timestamps convey different water quality parameters, and also tells the farm status in shrimp culture monitoring. So if you're taking a multispectral NSR, and then you're trying to merge it, and if multispectral is not available because of the cloudy situation, you may not end up doing the right kind of analysis for the shrimp ponds. Hence, acquiring images from two different satellites, merging it, and doing data fusion is challenging. Now, Galaxy has come up with a solution, wherein we are pioneering the most accurate and consistent data sets from space through putting together a multispectral and a SAR sensor together on the same satellite and acquiring images at the same timestamp with the same look angle and with the same perspective or the overlapping perspective. And hence, for some part of the maritime monitoring, the tip and queue can be merged into one. Natural catastrophe events loss analysis can be captured in 3 days as opposed to 2 weeks, and shrimp culture monitoring will be more consistent. How do we ensure consistent imaging? So let's just do a quick comparison, right? Now, when you don't have any clouds, you have a regular cloud-free day. On that day, your optical and SAR or a multi-sensor image would essentially have a similar output. You will have a building identified, you will have a pond identified. Object detection is seamless in that situation. But let's say it's a cloudy and a foggy day, right? Then, your multi-sensor will give you some outputs, while your cloudy day images will not be able to give you the accurate outputs because of, non-visibility of the entire area. If you take nighttime, optical or multispectral will effectively not have much of a visibility around it, and hence the detection and regeneration will be very difficult. But with multi-sensor, it will be there. Now, multi-sensor, although is there, but during super heavy cloudy situations, in the multi-sensor stack also, multispectral image will not be available. Only SAR will be enabled, will be available. So hence, how do you solve that last mile problem of being available and consistent all the time? Generative AI is the way forward. So it helps you to become highly available and easily interpreted. Now, what do? We take the training data, which we are acquiring on a cloud-free day, right? And we take the new data. Let's say optical is not available on that day. Using generative AI, with the new SAR image, we regenerate a visual data so that you have an optical equivalent SAR image, right? So traditionally, people and scientists and everyone community has tried to do false color composites of the SAR image, right? Although it's not very, very accurate, or it's limited useful even today. But with this regeneration of an optical equivalent with Drishti sensors will be much more useful, will be much more accurate, near to the real conditions. Right. Hence, so after removing the clouds, the final mergence of or final merger of optical and SAR will be available to the end customer. Now, this all is being done or is going to happen by a satellite which is going to go into space, which has a multispectral and the SAR sensor together. We are calling that as Mission Drishti. Now, Mission Drishti has a hybrid SAR plus EO sensor with a miniaturized satellite form factor, largely energy optimized. It'll be all-time, all-weather imaging. It'll be agile to move left and right while capturing images, and there'll be an edge analytics and processing also. That'll be done on top of it. A little bit about the satellite. The first satellite that we are going to send up is we are preparing for the launch, and we're in the final stages of our DDR, I would say, of post CDR, and currently we have a resolution of 2 meters in SAR. Imaging modes are spot, sliding spot, and strip. Polarization will be VV. Swath will be around 30 kilometers. NESZ is minus 15 dB. MSI payload at the same 2 meter resolution. There'll be 7 bands, pan plus 6 multispectral, and the swath will be around 10 kilometers. Orbit will be LEO, somewhere around 450 to 500 kilometers. Be SSO, which is effectively sun synchronous orbit. And the satellite size will be pretty small. It'll be a CubeSat, not a CubeSat form factor for sure. It'll be a pretty large in that sense, which is 1 meter cross 0.8 cross 0.83 meters. And the satellite mass is going to be 145 to 150 kgs. The antenna will, of course, come out. So this is a non-deployed form factor of the satellite size overall. So in a nutshell, we are trying to enable data fusion to happen in the most right way. And, hence we understood why data fusion is not something that is being, in a commercial context, we're able to do. We are solving that problem by building a Drishti satellite and hence trying to fix many of the challenges that a developer would face to make and develop as many as applications as they want. So I wanted to keep it a little more short and brief, but happy to take any questions and move forward. But thank you so much for the opportunity, everyone, INAA, NEAK, and Suresh sir. Thank you so much.
Okay, thank you, Suhas Singh. I think it was a very short and sweet. You are talking about the imagery intelligence where you want to combine the multiple sensors and also brought out what is really involved in data fusion. And nice to see that you're trying to really combine them, bring you what you call consistent imaging using the hybrid as well as the cyber SAR as well as the Earth observations. And Drishti, it's a very nice name. Hope that everything will come. I think now it is the time for question and answers if there are any. And I have gone to the chat box. There is one question which has come from the Korean side, and it is to Dr. Nilesh Desai. Is he there? Yeah. Question
Yes,
is,
sir.
I will just read out. Please let us share if you have any predictions about climate change based on the snowfall and glacial changes in the Himalayas, as confirmed by satellite images and AI. Can you throw some light on this, Dr. Nilesh Desai?
Yeah, so as I suggested, you can have a look at our Veda's website where we have showcased some of the results obtained for this particular glacier and snow related applications. So most of them are in open domain only. So we welcome that collaboration if at all we are interested in. And many of our satellites are being utilized for various observation which we do using many of these satellites. And then we do the processing. And now, as I mentioned about the landslide as well as the glacier studies, we have this taken up a project in Ladakh also on similar lines. So we are open to any collaborative efforts related to that. And as per the data policy 2023, whatever data is freely available, that can be easily shared among India and Korea.
Okay, thank you. There is one question in Korean language. I would request my co-chair to look into that.
Okay, thank you
Juan
for
Cho or something, yeah.
okay, thank you for taking care of the question from our side. There's no any other question except I may just throw a question to our recent speaker, Mr. Singh from Galaxy. Are you ready to answer my question? Okay, it's a very simple question. Looks like everyone is working hard toward utilizing images. Okay, so it looks like consistent imaging is a big deal. Consistent imaging. How accurate is the processed image versus the realistic, what is happening? So may I ask you, so what are some efforts to quantify those processed images? Is there some numbers we can share? Is there any strategies to make sure that the processed Gen AI-driven images are in fact true? Let us know.
I think I'll be able to share the quantification, maybe a little more in closer one-to-one setting. But just to give a color on the context here, so when if you talk about spatial and temporal matching, it is pretty accurate. The only thing that may not be super accurate is the spectral regeneration of the images, right? So we can only regenerate an optical equivalent, but I cannot go and regenerate any other bands in the entire EM spectrum of the entire, of the entire spectrum. So from an accuracy standpoint, geometrically, it'll be accurate up to 96+%. From an optical equivalent accuracy standpoint, again, it'll be pretty accurate because during the training set that we acquire, the training set has been acquired in a more consistent fashion, and hence, there are very lesser anomalies and less errors in training the data set. When you train a data set from two different satellites, your timestamps are different, your angles are different, your perspectives are different, and many other fundamental level of data acquisitions are not similar. But with Galaxy's own training data set, you achieve unparalleled accuracies and unparalleled, combination of imageries that you can get. So quantification certainly much better than what you can do on a standalone data set. But I'll be able to provide more colors on that once we do one-to-one interaction.
Okay, thank you for the great answer. Okay, so I don't think we have any more from our side, unless Dr. Shresh, can you go ahead and say something to close?
No, I have one or two questions to Dr. Nilesh Desai. I noted down certain things like Dr. Desai, you said in Dyson LWR spectrometer, I saw that one bullet says mimics human. I got interested. Can you throw some light on that?
Can you repeat, sir? I didn't get the
Dyson LWR spectrometer, that event-based activities, one bullet says it has certain qualities like mimics human or something. I got really curious to know what it is.
Event-based detection? Yeah.
No, just below that, something like that. I saw that. I hope it was right.
So we have this neuromorphic camera system, sir. So that will detect the change only and transmit the relevant change part only while imaging. So
No. What is the special features of that camera? Anything specific to that camera?
So it is in-memory computation. There is a device called memory stir. So that is utilized inside that. So that will have in memory the previous image, and then it will take the next image and try to compare the change detection, and then transmit only the change part of that. So you don't transmit all the data all the time. So that will preserve our data transmission bandwidth also. So that is a new trend happening now in the neuromorphic camera system. So we had one collaborative effort with the IISc team also, where a professor from IISc and suggested some collaborative areas. So this is one area, especially for lightning mapper, which we are trying to put on our geostationary orbit. This is the particular technology we are trying to adopt.
Okay, well, one more I have is, you said Rydberg atom-based receiver. What are the special features in that compared to the other receivers that we are having?
Yes, sir. So in place of the microwave receiver, which we are traditionally using in our synthetic aperture and other RF systems. So this is a Rydberg atom-based system. This is more on lines of the quantum-based radar technology. So you use this atomic clock technology for developing this Rydberg atom-based receiver. So that is being proposed for our future radar mapper. So you can fine-tune it for any frequency. Otherwise, for RF, if you have a C-band radar or an X-band radar or a L-band radar, I need to change the receiver all the time to cater to the RF front end. Here you can fine-tune it as per the requirement of the particular sensor.
Here emerging technology. You have some connection with IAST, on quantum communication. Anything is related to that?
Yes, sir. As a part of that National Quantum Mission only, we have proposed that to NQM for this technology development related to Rydberg atom-based receivers.
Okay, now, coming back to Galaxy High, you said data fusion. How many numbers of data you are handling there? Is it only 3?
So it's 2.
2 only.
Yeah. Multispectral and SAR.
Only 2, is it?
Yes, sir.
Generally, people handle, when we talk about data fusion, sometimes 8, sometimes 10 of different frequencies, different amplitude and all that. It becomes very complex. What is the complexity in this case when you are handling only 2 data sets? That is your SAR and maybe Earth observations.
So when we do SAR and multispectral, the major things that we are trying to bring together is the amplitude information from SAR and the DN values from multispectral. The complexity really lies in the geometrical aspects of the pixel size of both the sensors and then the perspectives at which the imaging is really happening. So from geometrical aspects, I would say largely the biggest complexity happens, and then from a time level, right? So the capture mechanism of a multispectral is to capture photons, and that will be at a certain timestamp. From a radar perspective, it will have its own timestamp. So matching the time and geometry is a real complex event to be done.
Okay. Any other question? Anybody else?
I'm seeing one question in the chat box.
Can you read it?
Yes, I'll read it out. It is from NAEK speaker Yong Park to everyone. Yes, the generative AI can produce visibly impressive image, but I am wondering how useful the generative AI is for a serious problem such as change detection. This is a question to Dr. Suresh from Galaxy.
Slight correction. I'm not Dr. Suyash. It's still Mr. Suyash. Thank you so much for the question. Yeah, I think, to be honest, data fusion or generative AI or any such blending of couple of satellite imageries will kind of have a bunch of errors in the entire analysis. Now, here we are not purely using generative AI, right? Generative AI is one part for the end user to really visualize the entire mechanism or the entire imagery. The real model has a physics-based or a computer vision-based matching of the two images, finding out what are the changes, and then visualizing that using generative AI. So, because generation will never tell you what is the change detection. It is largely the computer vision that is going to tell you really what is the change detection that's going to happen, right? Because NDVI in a way is also a way or a means of computer vision technique, but more of a geospatial computer vision technique to bring the right thing coming out of it. So I would say generative AI here is a tool to really visualize for the end user to understand the context in a SAR imagery. But under the hood, it's really the mix and match of multispectral DN values to the amplitude values of SAR using computer vision techniques to bring the data fusion alive.
Okay. Do we have any more question in the chat box? Anything? Maybe that's all, right?
Yeah.
Okay, so would Dr. Lalit Nambika want to make a final concluding remark before we end the session?
No, we will give the summary of the
Yes, sir.
presentation. Basically, we had 4 presentations, and all of them were on the Earth observations. And the first one from Korean friends, I think, is about the cooperation between the Korea and India, how we can really explore the joint satellite application. It was very interesting. And I'm sure that there are avenues which are open. One can really take it up. And of course, one can see the kind of very comprehensive developments which are happening in India, particularly at Space Application Center on various payloads and associated technologies. I think it was really a feast for all who participated in this program. I'm sure that you can take it further and have dialogue and discussions with them. Then, of course, the next one was again from Korean. It was on the how we can leverage the high resolution imaging for coastal water issues. This is one of the very important areas, and a lot of good work has happened. I think they've made a quick presentation, and this sort of combining the multiple sensors and coming out with an idea of Drishti by our youngsters as a startup they started. I think it's a very novel idea. When are you planning to launch it really? Any possible date is available or time frame?
Most probably mid of next year.
Good. I think, really brought very interesting. And before I conclude, I would like to really thank each one of the authors. They made an excellent presentation and really brought to limelight the various spectrum of Earth observations. I think it was very rewarding for all the people who are attending this. And also, I believe this must be available in the recorded forum for anybody else to look at it and then understand further. So let me also thank the organizers for giving us an opportunity to participate and then trying to learn something new. So over to my co-chair, if he has anything he can add, otherwise to Lalitambika.
Okay, well, no more from us, so you can go ahead and make your final comments to close our session.
Okay, over to Lalitambika.
Thank you so much. And let me thank the two session chairs for conducting it so beautifully, and all the speakers and all the participants. And just requesting you all to be available with us tomorrow also, because we are going to have the second day program starting at the same time as today. And that's going to be more on the policy aspects and on examples of several startups who are actually using this data. So, thank you. Thank you.
Thank you. See you tomorrow.
See you tomorrow.
Bye. Bye.
Thank you.